Hello everyone, these are the discussions about the universe. My name is Samuel, and as usually, Norby Werner is here with me. And today we have Bharat Ratra, our dear guest. Welcome.
Thank you. It's really nice being here. It's my first time here. And I really enjoyed the visit and meeting people.
So to begin with, I would classify myself as a theoretical physicist. Norby is astrophysicist. How would you classify yourself?
I started out as a theoretical physicist working on string theory and quantum cosmology, and then gradually transitioned to work on regular cosmology. Mostly because, I found string theory very, very interesting, but my view was that it was a consistent way of doing quantum mechanics and general relativity, which was very, very difficult to do before string theory came along. But I didn't think that we would be able to get any real predictions from it that could be compared to measurements in the 20 or 30 years that I would be active, and I wanted to try to do something which could be compared to measurements, and that was my main motivation to switch to cosmology.
You used past tense, like you didn't think we can make some predictions from string theory. Do you think we can do it now, or?
I haven't carefully kept track of it, but I figured that if there was some really strong prediction that related to fundamental consistency of quantum mechanics and gravity, I would have probably heard about it, and I haven't heard about it so far, so I don't know.
And people claim it as one of the successes of the string theory, that string theory predicts gravity. From your point of view, isn't this impressive prediction, or is it just unimpressive post-diction?
It's well, I guess it has so many degrees of freedom that it does include a spin to graviton. And I don't know if that would be the most interesting thing to me. It's kind of a consistent way of doing quantum mechanics and including gravity, and we have no other way of doing that right now. And I don't know if that means that string theory is the correct description, or we just haven't searched enough.
Okay, but fortunately today we aren't discussing string theory. We had a previous episode about it, so today we'll be discussing cosmology and the presence of dark energy. So do you have some brief summary of what is the current understanding of cosmology?
So we have what's known as the standard lambda CDM model, and dark energy there is a cosmological constant, and it doesn't vary with time. And the CDM stands for cold dark matter. And this model was kind of probably first looked at very seriously in the mid-1980s, when there were some indications that maybe the universe was older than you would expect given the measurements of the Hubble constant you had then. And adding a lambda helped increase the age of the universe. And it turned out that maybe about 15 years later, when people were looking at type 1a supernovae, they found another prediction of this model to be true, that it predicted that not only does the universe expand, but the expansion is speeding up as a function of time. And I think that's when most people started taking it much more seriously. And so far, pretty much all the measurements we've had since then, since the late 1990s, have been roughly consistent with the dark energy being a constant, a time-independent constant. And the lambda CDM model, which now usually is taken to have 6 free parameters. So one of them is the density of ordinary matter, or what cosmologists call baryonic matter. And that's basically the density of atoms and molecules. And another one is the density of cold dark matter. And there's some other parameters that characterize the shape of the spectrum of the bumps in the microwave background and a few other parameters. And it seems that with these 6 parameters, given how precise our measurements are right now, the model can't be ruled out. There's some issues with it, and I mean, you've probably heard of this thing called the Hubble tension, where people have measured the expansion rate or the Hubble constant, and they measured it at low redshifts that's around us in the nearby universe. And some of these measurements suggesting that it's expanding a little bit faster now than if you'd measured the Hubble constant using the microwave background measurements at much higher redshift. And there's a few other issues like that. But I guess, at least in my opinion, they're not really strong enough to discard the model at this point. But we have a lot of theoretical reasons, which might just be speculations that want us to kind of go beyond this model with just a constant dark energy density.
So if I summarize what our viewers are probably familiar with, is that from the total content of the universe, matter is about 30% and dark energy is about 70% of the content of the universe, and out of the 30% of matter, 25% is dark matter, or most of it is dark matter, and only 5% of the total content of the universe is normal matter. So I think it's good to spend today's episode talking about the 70%, about the dark energy. Usually when people talk about dark energy, they talk about the cosmological constant lambda that was first introduced by Albert Einstein. And as you mentioned, this cosmological constant is constant with time. And you say that there is no good reason to assume that it should be constant, and there might be actually very good reasons to assume that it is not constant, that it is changing with time. So what are the main motivations for the dark energy changing with time?
Okay, so the motivations are mostly theoretical. So there's a number of kind of interrelated ones. So one of them is that if you just have this constant energy density, the cosmological constant, then it's very difficult to tie that into other parts of physics, which are usually described in terms of dynamical fields. Like if you take the standard model of particle physics, we have quarks and we have leptons and we have the Higgs field, and there's nothing there on the face of it that looks like a constant energy density. And so maybe we could tie in these cosmology observations to the standard model of particle physics if we postulated a new dynamical field to describe the dark energy. And the simplest thing to do is to postulate a new scalar field. And I mean, very superficially, if you're thinking about this in a non-relativistic way, the temperature in this room is a scalar field. It's slightly different in different parts of space. I mean, near us, it's probably a little bit warmer, and so the temperature's a little bit hotter. And maybe in the center of the room, it's a little bit cooler. And depending on how you heat up the room, that temperature changes as a function of time. And we're going to generalize this to something that's consistent with relativity and look at a scalar field somewhat similar to the Higgs field, which is a scalar field. But this dark energy, dynamical dark energy scalar field can't be the Higgs field because it interacts too strongly with other things. And one part of the name, it's dark, so if it interacts with other things like atoms or molecules or electrons, it's also going to emit and absorb light, and it wouldn't be dark. So we know that the dark energy can't interact much with normal matter, and so it can't be the Higgs field, but mathematically it's got the same sort of properties as the Higgs field, except if you think of it in terms of how heavy the particle would be, the Higgs boson mass that corresponds to the dark energy particle would be much, much, much smaller, maybe something like 44, 45 orders of magnitude lighter, because we wanted to have a very, very, very smooth potential, and the steeper the potential you have, the more massive the field is. It kind of oscillates back and forth, and we don't want the dark energy to do that, and we can talk about why we don't want that to happen. But
now, there is a naive question, and some people might find this confusing. We distinguish between matter, either visible or invisible or dark, and energy. And if there is one equation people know, it's that E equals mc squared. So how to distinguish those two apart?
Yeah, so it's kind of very, very unfortunate that this hypothetical substance, which was introduced to basically preserve Einstein's general theory of relativity on cosmological scales, that it was given this name dark energy. So the dark part is pretty clear. It doesn't interact with light, and so we don't see it. And in that sense, it's similar to the dark matter, which also doesn't interact with light, and so we don't see that. But this is not energy in the sense of kinetic energy or energy of motion or electromagnetic energy or nuclear energy. This name was chosen to distinguish it between matter from matter, because we had normal matter which interacts pretty strongly with light, at least when you have electrons and protons, and dark matter which doesn't interact much with light. And the dark energy doesn't interact with light, but it should just be called a dark substance or dark something, but I guess energy is more catchy. And the difference between dark energy and dark matter, so if we think of them in terms of particles, the dark matter particles are almost certainly going to be pretty heavy, maybe 100 times as heavy as the proton or somewhere in that range. But the dark energy particles are going to be much, much lighter. And the reason we want it to be this way is because when we look at observations, we see that there's dark matter associated with galaxies and even on smaller scales. So gravity has been able to gather up the dark matter, and that means the dark matter, at least in the simplest models, when you look at what's called weakly interacting massive particle models of dark matter, those guys are pretty heavy, and so they can be pulled together by gravity. But we don't see dark energy on the scale of galaxies. To see dark energy, you have to go to much, much larger scales, like typically hundreds of times the scales of galaxies, or thousands of times. And so we don't want these particles that make up dark energy to be heavy, because if they were heavy, then gravity would have pulled them into galaxies and clusters of galaxies, and we'd see the dark energy there. Excuse me. Instead, we want them to be very light, and in that way they behave like very relativistic particles. They move very fast, and they have a lot of kinetic energy or energy of motion, and gravity can't pull them together. But the heavy dark matter particles, they're very heavy, they're non-relativistic, and they're hardly moving at all. And so gravity can overwhelm their kinetic energy of motion and gather them together into clumps.
And those Those particles would be like quanta of the dark energy field, or?
Correct, yeah.
Okay.
So it's like a scalar field, and when you quantize it, there'd be particles. Just like when you quantize the Higgs field, you get the Higgs boson, the particles there. And this would be a scalar field particle also.
So when you say that the dark energy is evolving with time, does it mean that dark energy was even stronger in the past, and it is becoming? What are your predictions? Is it becoming weaker with time, or?
Okay, so people have looked at both options, where the energy density of the dark energy is decreasing with time as the universe gets older and older, and where it increases with time. And the observations now, most of them seem to suggest that if it's changing with time, its energy density gets lower with time. But when you go back in time, so in this case where it gets lower in time as you go forward in time, when you go back in time, its energy density increases, excuse me, but the energy density in atoms and molecules and charged particles and the energy density in the cold dark matter increases more rapidly as you go back in time. So even though the dark energy is getting larger relative to its value now as you go back in time, the energy density in dark matter and in baryonic matter is getting much, much larger than they are right now. So they become more dominant relative to dark energy as you go back in time, even though all three of them are increasing as you go back in time.
So if the energy density in dark energy is decreasing as a function of time, I mean, dark energy will still dominate in the future, but it's
because it decreases more slowly than the energy density of atoms and molecules and the energy density of cold dark matter, and so it would continue to dominate.
So what would that mean for the future of the universe?
So if you have just a cosmological constant, then it's really easy to do the math. And I mean, this is kind of really pretty speculative, because if you kind of think about it, we're living at a time where the dark energy density is maybe a factor of 2 or 2.5 that of the density of matter. And so if you kind of think about going back maybe 5 billion years or 10 billion years in the past, the dark energy density would have been much, much lower relative to the energy density in dark matter. And we would have never seen it because our equipment, our measurements wouldn't have been precise enough. So I am going to try to predict the future, but it could be that there's something that's subdominant now, and maybe 10 billion years in the future, it's going to be more important relative to everything that's redshifting away. But if you want to predict the future, you can make some assumptions. You can assume Einstein's theory of general relativity, and you can assume you've done all the measurements that you need to do to determine the various components of matter, including dark energy in the universe now. And if we have 70% dark energy, if it's a cosmological constant, and if we have 30% in matter, and that's behaving the way we expect normal matter and cold dark matter to behave, then in the future, that normal matter and cold dark matter is going to become irrelevant relative to the cosmological constant, and we'll get an exponential expansion in time of the universe. And that solution of Einstein's equations is called the de Sitter universe. And so everything will be separating very, very rapidly. And eventually, the only thing we'll be able to see is pretty much our galaxy, and maybe things like Andromeda, but that's completely not clear. It depends when the transition happens, because Andromeda and the Milky Way might have merged by then. And that's all we'll see, because everything would be moved apart really, really far. And things will just be black, really dark. You won't see any other galaxies. But if it's decreasing with time, you won't get the exponential expansion, but you'll get something that's pretty fast. And qualitatively, it should be similar, but maybe at a longer time in the future than it would happen with the cosmological constant.
So you said that you can predict the future if we done the measurements correctly, but currently it's very difficult to distinguish between models of dynamic and static dark matter. Now imagine there is a phone call from a billionaire and he says that he has $1 billion to spend. We want to help you distinguish between different models. What would be the observation to fund that can help us?
Well, if you are being somewhat conservative and you want to be sure you're not wasting the money, then probably it would be looking more precisely at these bumps called baryon acoustic oscillations. So if you go back to the early universe and start out in what's known as the inflation model of the universe, where you have, again, a scalar field which is called the inflaton, and it has a potential energy density that's relatively flat. So it has an energy density that's almost a constant, and so you get accelerated expansion there. It behaves like dark energy, and that's called inflation. And if you look at the mathematics, it turns out that as you go back in time and look at scales now, say the scale of the distance from us to a galaxy, a billion light years away. As you go back in time, because the universe expands as you move forward in time, as you go back in time, that distance shrinks. And we can go back far enough so that distance will be smaller than the solar system, and we can go back even further when it'll be smaller than the Earth. And you can go back even further when it's smaller than an atom, and even further when it's smaller than the nucleus of an atom. And we have physics equations that work at all those times. So we're pretty certain that this actually happens, that the whole observable universe now was once smaller than an atom and much smaller than a nucleus of an atom. And so when you get these things to be so tiny, you have to worry about the other foundation of physics, which is quantum mechanics. And there's a fundamental principle in quantum mechanics called the Heisenberg uncertainty principle. So one way of expressing that is that you can't measure the position and the momentum of a particle to arbitrary accuracy. But another way of expressing that Heisenberg uncertainty principle is that you can't measure the energy density and time, the energy and time to arbitrary precision. And so if you are looking at things over very, very short time scales, you can have large fluctuations in energy. So you could have particles popping out in different parts of the vacuum, provided they come back and annihilate. So you could produce pairs like, you could produce an electron and an anti-electron pair and violate energy conservation, provided you do that over a really short time, and they'd pop out. And so you'd have regions in space where maybe you have one particle more and the neighboring region has one particle less. So you have a little bit of excess mass here because you have more particles and a little bit of less mass here. And gravity likes gathering mass together. So because you have more mass here, so one says gravity is unstable. So I don't know if I have anything to drop, but I can try dropping something. If I can find something that I can't break.
And drop the glass.
Yeah, that'll be pretty dramatic. Okay,
you can drop my pen.
I got a coin here. So this has got a mass, and the Earth's got a mass. And if I don't support this, no, I won't. I hope I don't break the glass. But this is going to be pulled towards the Earth by the Earth's gravitational field, and the Earth's going to be pulled towards this because this also has a gravitational field. But the Earth's much more massive, and we know from Newton's second law of motion that the acceleration is proportional to is equal to the force divided by the mass. And because the mass is much greater, the Earth doesn't move that much. But if you go back to this inflation model where you have a little extra mass here and a little underdensity here, then this guy is going to have a stronger gravitational field, and it's going to pull stuff out of the valley, and it's going to grow. And if you draw this in terms of energy densities, where the height represents how strong it is, then the peaks are going to grow and the valleys are going to drop. So you'll start across in space, you'd have regions where you have peaks and you have deeper valleys. So the rich are going to get richer and the poor are going to get poorer. And gravity is going to gather this stuff together, and eventually it'll get really huge. And so you think that's how you formed bumps in the galaxy distribution and in the microwave background. So you have these masses here, and the microwave light goes through them, and they bend, and they dip into the potentials. And so while this is happening, the universe is expanding, and all this stuff was happening on scales outside of what's called the horizon. That's the distance, or the Hubble radius, the distance over which we can see things, because we know that the universe has a certain finite age, and we know that the speed of light is finite. So the furthest you can see in a certain amount of time is the distance you can send the fastest thing to, and that would be the speed of light times the age of the universe. And that kind of ignores the expansion of the universe. But when you do this correctly, by including the expansion of the universe and doing the integral instead of just doing the multiplication, you can see a little bit beyond what you would think is the horizon, which would in principle just be 13 3/4 billion light years. But you can see up to maybe about 40 billion light years. And so there's stuff happening in these inflation models outside the Hubble radius now. And as time goes on, they kind of come in because the universe expands, and you can have causal effects going on. So once you get stuff into the Hubble radius, you can gather stuff under gravity, and you push things together, or actually gravity pulls things together, and it pushes up the pressure, and that pressure doesn't like that, and so it pushes back, and so you have mass coming in and then going back out because you get these oscillations. And you can see these oscillations in the microwave background, and if you've seen the past spectrum of the microwave background, they're pretty prominent. And you can also see these in the distribution of galaxies when you transform this and look at it in Fourier space. And these are called baryon acoustic oscillations there. Because the dark matter doesn't interact with the light, which is what's responsible for pushing the stuff out, these oscillations in the matter distribution are much, much smaller, and they're much more difficult to see. But they were seen for the first time, I think, in 2005. And we understand the physics very well there, so it's very, very clean, and you can calculate things in linear perturbation theory and do a systematic expansion. So it's very clear physics, and if you can measure the peaks in the baryon acoustic oscillations, they tell you basically the size of the Hubble radius or the acoustic horizon at very early times. And once you know that, and you can measure the angle, you can do a lot of things. You can measure the expansion rate, you can measure the contents of the universe, and you can do this at many, many different redshifts depending on what galaxies you're looking at. And you can go from a redshift of 0, which is like now, to maybe hopefully a redshift of 3 or even 3.5. And there's a bunch of experiments that are coming online or taking data now. And one of them is the DESI experiment, the Dark Energy Spectroscopic Instrument. And that's going to measure the redshift of a lot of galaxies and quasars. I mean, till I think this year or maybe last year when DESI turned on, we'd measured redshifts of about 3 million galaxies. And if DESI works according to plan, they'll probably measure redshifts of 40 million galaxies and quasars. So that's almost 1.5 orders of magnitude more than everything that's been measured so far. And maybe that's going to be groundbreaking enough. And if it isn't, then I'd probably spend the $1 billion on an upgraded version of DESI and try to collect more data and go to higher redshift. And I mean, that's kind of a really interesting thing because it measures things in 3 dimensions, unlike the microwave background, which is kind of a 2-dimensional experiment.
So this would be very useful to understand the structures which are leftovers of the earliest stages of the expansion, to measure them as accurately as possible. And you coined this the conservative investment. So what would be the high risk, high reward billion investment? So
we have really good, we will have really good data from redshift of 0 to maybe 3 or 3.5. And we have really good microwave background experiments at a redshift of 1100 or so. I mean, there's some issues in the microwave background. So one thing is, I mean, we're going to get very, very good microwave experiments from the ground, like at the South Pole and in Atacama with the Atacama Cosmology Telescope. And the South Pole, it's the South Pole Telescope. And in the near future, there's this thing called Simon's Observatory, which is also in Atacama. And that's going to give you really good measurements of the microwave background. But unfortunately, they're not going to be able to do the whole sky because the Earth's going to block them. And so they have some limit to what angular scales they can probe. And there's larger angular scales that we can only probe from space. And maybe that's a useful thing to do. So the problem there is that if you look at both the Planck results and even the WMAP results, which is another microwave background satellite experiment before Planck, you see that at very large angular separations, there's almost no power in the microwave background. I mean, if you're looking at this in multipole space, there's the quadrupole, which is the lowest one that's associated with the primordial microwave background. And that seems kind of suppressed quite a bit relative to what you'd predict with the standard lambda CDM model. And that it would be really interesting to kind of look at that more carefully. But that's kind of a really complicated region to look at because our galaxy emits in the microwave part of the spectrum, and it would act as a foreground that contaminates the primordial microwave background. And so we'd have to do better foreground analysis and maybe get more microwave background data. And I don't think you can do that with $1 billion. But in between the redshift of 1100 and 3 or 4, there's a huge part of redshift space that at present we don't really have ways of probing. There are some experiments, so you could do things like reverberation measured quasars, which I've been doing with a collaborator here, Mikhail, and you can maybe go up to a redshift of a little beyond 3. And if you go with starburst galaxies, maybe again you can go to a redshift of maybe 3.5. And if you want to go beyond that, you could try X-ray and UV correlated quasars, which you could probably go to a redshift of maybe 6, or gamma ray bursts, where you can go to a redshift of maybe 8 and maybe even higher. And maybe if those things can be made into cosmological probes, that would be a good place to spend $1 billion to probe this redshift space from a redshift of about 3 to about 1100.
So fill in the gap between.
Yeah.
But it's probably very difficult because not much was going on in the universe in between. Yeah. I don't want to call it the boring part of our history, but it's the dark ages. So
yeah. But you might see gamma ray bursts all the way up to a redshift of 15 or something. So there's still quite a bit down here that you can look at. And yeah, I don't know. But I mean, gravity was still acting and these density perturbations were growing.
So unfortunately, we probably don't have the billions of dollars to spend on experiments. That means we have different theories and not something to distinguish between them. So in some areas of physics, I won't be pointing fingers, this happens, like we are lacking evidence and we just keep getting new theories. Do you think this is the case in cosmology, like the speed of theory got so fast that it's outpacing the experiment and stop being so productive as before, or not so much?
So it's kind of really difficult to say. I mean, maybe with DESI, you'll measure everything and you'll get the expansion rate to a redshift of 3, and you'll find that it's consistent with more precision with the cosmological constant. And then you're not really sure what to do. I mean, do you try to get more experimental evidence and tighten up the error bars? Or maybe with DESI, you'll find that it's consistent with some kind of dark energy density changing with time. And that'll completely shift the field if that happens. And I mean, if you go back and look at what happened with baryon acoustic oscillations, I mean, from the time they found the microwave background till around the bumps in the microwave background, not the absolute temperature measurements, but till about 2005, that was the most interesting probe for cosmology. And then suddenly you got this new probe, and it's kind of starting to become the most dominant thing. So we're not sure whether something like that could happen again, maybe next year, that somebody will find that you have a way of calibrating or using gamma ray bursts, and you can turn them into a very precise cosmology probe, or you could do this with quasars and turn it into a very precise cosmology probe. And I mean, we don't even have to really understand the basic physics, because for the type 1a supernovae, we don't understand the physics that well, but we see enough correlations, and we can consistently look at that data and use it as a cosmological probe. And maybe one of these things will happen. And if it doesn't happen, then I guess cosmology is going to become like a more philosophical thing than physics, I guess. And eventually that might happen, because maybe you're going to have to get to a point where your next experiment is $50 billion or $100 billion, and it's not clear that society is going to want to do that. And particle physics might be kind of approaching that point with the next collider.
I think some budget cuts
Yeah.
from humanity. And so the good thing about cosmology is it doesn't rely entirely on new telescopes, which we have to wait for decades. Maybe just a good idea of new thing to have a look at, or something rediscovered in old data. And speaking about having new bright ideas, you are one of the authors of the idea of the dynamical dark energy. I'm just trying to figure out, like, what is the reasoning behind it. For example, why wasn't you satisfied with constant dark energy, or was it like there is a quantity that is very small but non-zero, so we have something to explain, or what is the line of reasoning you take when?
So one of it was that you want to try to tie this to the rest of physics, like the standard model of particle physics. I mean, there was a couple of other motivations, and it's not clear whether these are really physical motivations or they're just kind of people's opinions. So if you kind of look at the energy density in matter now, it's roughly a factor of 2.5 smaller than the energy density in the cosmological constant. And if you go like a few billion years in the future or a few billion years in the past, that ratio is going to be very different. In the future, the matter will be much less important than the cosmological constant energy density. And in the past, it was closer together. And we don't understand why we showed up at this point in time where the matter density is roughly comparable to the dark energy density. And maybe you want to try to have them both evolve in time so they're a little bit closer at all epochs of the universe. And the other thing you might be interested in trying to do is getting rid of the energy scale associated with the dark energy now. So if you have a constant dark energy density, that's an energy per unit volume, or an energy over a length scale cubed. And when you think about this in natural units, dimensionally, that's an energy to the fourth power. And so if you take the fourth root of this energy density in the right units, it defines an energy scale. And that energy scale is roughly a few millielectron volts, which when this first showed up in the 1990s, there was no fundamental physics happening at that energy scale. And so that kind of disturbed some people. If you want to introduce a new phenomenon and you introduce a related energy scale, maybe that's not the reasonable thing to do. Maybe you want to try to tie this into something happening at a higher energy scale. And so if you allow the dark energy to decrease in time, as you go back, it increases in time. And if you take that fourth root at an earlier time when the dark energy is increasing in time, it'll correspond to a higher energy scale. And if you go back when the universe is maybe 100,000 years old or 5,000 years old, it could be much, much, much larger. It could be billions of electron volts or trillions, and you could tie it into models of particle physics there. And it's just gradually dropped as time has gone on because the dark energy density has decreased, and it's dropped to a really, really low value now. So we don't worry about this in the baryon density because we know that all that baryon physics, I mean, it's been kind of developed at much hotter times when the universe was much younger and much denser, and that's where the fundamentals physics has been going on. And then as the universe has expanded and cooled, the energy density in baryons has dropped. And so there's kind of this hope that maybe the dark energy behaves the same way. But it's kind of unclear whether this is just speculation. But I guess you sometimes have to speculate and then kind of build models and make
every scientific idea begins with a speculation. So
yeah.
When I was a high school student and I was reading books about cosmology, then the big question was always whether the expansion of the universe will go on forever, or whether there will be or whether it will stop, and then there will be a big crunch. With the discovery of the accelerated expansion of the universe, it looked like we can pretty much rule out the big crunch. Now, if we include dynamical dark energy, is there still room for a big crunch, you think, or
I'm sure you could build mathematical models. So, I mean, a few years ago, maybe like 10 or 15 years ago, people were actually thinking of the opposite thing, that the dark energy density was increasing as a function of time as we moved forward, as the universe got older. And there, instead of a big crunch, you get a big rip, and it expands faster than exponential. But I think it's pretty clear now that that's kind of pretty unlikely, unless there's some subdominant dark energy now that's going to start dominating in the future. But if we don't, if we think we know all the components that contribute to the stress energy tensor in Einstein's equations, then I think that big rip is really unlikely. And so right now, if you take the lambda CDM model it's probably just going to expand exponentially forever, and we're not going to get a big crunch. But I don't know if the error bars are big enough to give you a big crunch. But I mean, there could be some hidden errors that people haven't correctly determined so far that still lets you have your big crunch, but doesn't seem that likely right now.
So I think, thinking of the past, let's say 30 years, I think there was a huge development in observational cosmology. Samuel just asked a few moments ago whether cosmology is observation or theory driven. So I, as an observer, my view is that the observations are improving so much that there is a very, very big observation driven element to cosmology. People are talking today about precision cosmology, where cosmological parameters are being determined at a, we're getting to a percent level. So it's really much better than 30 years ago. However, determining whether dark energy is constant or changing with time is difficult.
Very difficult.
It's difficult, and there is this parameter, the equation of state parameter of dark energy, which if it is the cosmological constant, then it is -1.
Yeah.
And observations are converging.
Yeah.
To this value of -1.
Yeah.
I think the hope is that it will be slightly different.
Yeah.
But the error bars are shrinking, and we are getting to this value of -1, right?
Pretty much. I mean, there's some indications that maybe it's not -1, but maybe a little bit more positive than that, so maybe -0.95 or something. But these guys, I mean, the error bars are still pretty big, and it's probably at the level of like 1 sigma, so 2 times out of 3 you'll get something that's not -1, and that's not convincing to anyone. But yeah, I don't know. I mean, I guess some of these scalar field models, which are more physically consistent models of dynamical dark energy, you can't really describe them in terms of this omega parameter. And so maybe if you do your data analysis with one of the scalar field models, you can find that it's dynamical, but you wouldn't see that with this fluid model where you have this omega parameter. And so I think it's kind of really useful to analyze whatever data you have in terms of many, many different models and see if they all are consistent with the cosmological constant limit, or some of them are and some of them aren't. And it's possible that maybe some models will give you some indication that they're favored. But
yeah, so I think the next decade is going to be interesting with new instruments, like, as you mentioned, the DESI, the dark energy spectroscopic instrument, and also the LSST, the Large Synoptic Survey Telescope, now called Vera Rubin Observatory. So there will be even more data, and maybe we will discover some differences from the expectations. So today you were talking about the curvature of the universe being slightly different from flat.
Yeah. So this is that like will be the curvature of the space. So if you kind of think of what the universe looks like in space at one instant of time, I mean, it could be completely flat, and it's kind of really difficult to think about this in 3 dimensions. But we live in a 3-dimensional space here. There's 3 axes, and to specify this point here, you set up an origin, and you might set it up in that corner, and you measure the distance from that wall and from the floor, and you need to specify 3 numbers to get its position here. And this is like a flat space. It's kind of difficult to think about this in 3 dimensions, but it's like the top of the table in 2 dimensions. It's a flat space, and if you extend it out to infinity in both dimensions, then that would be like an infinite flat space. And you can also have a 2-dimensional surface of a sphere, and that's a curved space, and it's got positive curvature. So it turns out you can choose either a flat space or a curved space, or what's called an open space, and that's kind of saddle-shaped, and it goes out to infinity. And you have these 3 different models that you can analyze using Einstein's equations. And depending on what data you use, most of them are consistent with the surface being flat. But when you look at the Planck microwave background data, it prefers the surface of a sphere, a 3-dimensional sphere. And it doesn't do that at a lot of significance, so it's kind of difficult to understand whether that's just a statistical fluke or whether when you have more precise data, it'll increase the strength of the signal. And so that's one thing I've been interested in trying to figure out, whether space is flat or whether it's positively curved. And again, like you don't get really strong statistically significant results, and so it's not clear what to make of it. But maybe when you get more precise data, you can get better results.
Speaking about the future, usually we build physical models by adding a piece by piece. So we start with a simple theory and then with a new feature into it to accommodate more data. So for example, the standard model of particle physics was built from the quantum electrodynamics by adding new fields. Sometimes we have to change the theory completely. So for example, the general theory of relativity isn't the Newtonian gravity plus something else. It's something completely different. Now, there are some efforts to change the general relativity. Eric Verlinde has his entropy gravity. There are some efforts to get the cosmology from the M theory. Do you think we are in for another large paradigm shift in gravitational physics? Or we are more or less set and we have to just add a bunch of tiny features and everything will be held tightly together?
So there's probably going to be a paradigm shift, but I don't know if it's going to come from cosmology. And the problem is we have these 2 fundamental theories that underlay all of physics, which is relativity and quantum mechanics, and they're mutually inconsistent. And maybe that's the way the world is, and you have these mutually inconsistent theories. But it would be really surprising that you don't have something that's consistent. I mean, and that's kind of, I think, the thinking of most people, that quantum mechanics and relativity have to be made consistent, and that's one of the fundamental motivations for string theory. I don't know if this is going to come out of cosmology, but I mean, that's where you have the strongest indication of this, because quantum mechanics predicts a cosmological constant that's 120 orders of magnitude bigger than what we see now observationally. And we don't see anything that strong anywhere else. I mean, you sort of see the Hawking effect where you get quantum mechanics and relativity again, but again, we haven't really seen Hawking radiation, but here we're actually seeing, I mean, if you assume general relativity is correct, then there is a cosmological constant or something like that. And your standard model of particle physics predicts something 120 orders of magnitude bigger. And that's where the biggest problem comes with quantum mechanics and relativity. And maybe that's where we should be focusing. And I mean, cosmology has gone through a bunch of revolutions. So in the early 1980s, when inflation came along, people focused on inflation models that expanded so much that even if you started out on a curved space, you'd blow up your balloon so much that you'd only see a really, really tiny part of it, and it would be effectively flat. So they said you can't have any curvature. And obviously you couldn't have a cosmological constant because quantum mechanics predicts it's 120 orders of magnitude bigger, and the universe would have been completely ripped apart and we wouldn't be here. And so there was no cosmological constant, no curvature, and so you had to predict a lot more dark matter, a factor of 3 more dark matter than you saw. And that's what people believed until, in some ways, I guess some people kind of got peeled apart from that. I mean, I guess Peebles was one of the first people maybe in 83 and 84. He would look at data a lot more than most theorists. And by looking at how fast things were moving, galaxies and clusters of galaxies were moving, he could measure the density of matter there. And he was finding it was 20% of the critical density. And I mean, now we know it's about 30%, but he was getting about 20% with large error bars on it. So he didn't believe that there could be so much dark matter. And so he kind of went back to putting in the cosmological constant. And that was kind of effectively ignored for maybe 15 years until the supernovae found another prediction from this model with the accelerated expansion. And so we went from a model that was completely dominated by non-relativistic matter, the dark matter, and the baryonic matter, to something where the dominant thing is the dark energy. And I think that was a pretty big transition. I mean, most of cosmologists kind of accepted that probably by the late 90s. And I don't know if something like that is going to happen again. I mean, if we can figure out why the cosmological constant is so much smaller than what quantum mechanics predicts, I mean, you'll get some kind of revolution there. And I don't know if it's going to come out of string theory, or it's going to come out of M theory, or emergent gravity, or it's going to come out of more precise measurements. And I mean, normally that's what happens. I mean, well, I guess, I mean, it depends how you look at things. I mean, if you look at the neutrino, the history of the neutrino, so Pauli kind of didn't want to give up conservation of energy and momentum. And so he said, let's introduce this really weakly interacting particle that compensates for the energy and momentum that we don't see in the particles we can get. And it took like, I don't know, 25 years before you could measure that. And dark matter is probably even more weakly interacting than the neutrino, and dark energy is probably even more weakly interacting than the dark matter. And I mean, I guess maybe if you have enough time and if you're lucky, you can kind of pin those guys down with much more precision. And maybe that'll kind of give you some clue to where to go, at least in your theory models.
So I have a concluding question. So you said that when you were starting your research career, you shifted from the string theory towards cosmology. Now, hopefully there are many students watching us right now. What would be your recommendation for them? What is the hot area of research right now or in the next upcoming decade?
So I guess you got to go look. I mean, so physics basically depends on theory and experiment having some interaction. And so if you have areas where it's very, very difficult to do the experiments and you're just going with a lot of theories, I mean, I'm not certain you're going to make a lot of progress there. And the same thing's true the other way. If you have a lot of experiments and your theory is too difficult to deal with, it's kind of unclear you're going to make a lot of progress. I mean, like, I guess turbulence is kind of one example, or magnetohydrodynamics. You can do huge numerical simulations and work in huge collaborations. And if you want to do something like that, that's a good area. But if you want to work in smaller groups, then maybe you want to look at areas where there's developments both in theory and especially in experiments and observations. And it seems astrophysics and cosmology is going to have a lot of data in the next decade. I mean, with even James Webb and with DESI and with the Rubin Observatory and Roman Telescope and Euclid. And I mean, these things are all supposed to fly, and hopefully at least most of them will work. And the other area where there's a huge amount of developments seems to be in biophysics, but I guess it's kind of seems to be a much more complex system to me than cosmology. And I mean, I'm not sure I have the ability to do something there. But biophysics has developed a huge amount in the last couple of decades, and maybe basic quantum mechanics seems to be developing a lot because you've got these really precise techniques that you can use and do precision experiments. And I mean, that seems to be a really exciting area, but I haven't really studied it that much.
It's uncommon to have the cosmology as the simpler option first.
It's the simplest thing to me.
Okay, so thank you very much. This is it for today's episode. You can find us online, just Google or type into YouTube discussions about the universe or Rozhovory o vesmíre for Slovak and Czech discussions, and see you next time.